Assalamu alaikum. This is lecture 4 of machine learning, and in this lecture we are going to explain underlying characteristics of linear and polynomial models. So if you look back at lecture 2 and 3, we have so far treated machine learning models and their training algorithms mostly like the black boxes. That means you have not explored any underlying characteristics of the algorithms and any underlying assumptions that you make about while predicting an outcome. So you have seen multiple algorithms and you can make different kind of predictions just by assuming the underlying concepts. However, having the good understanding about how things work can help you quickly get comfortable and maintain an appropriate level of understanding the model itself. And then you can find out the right training algorithm to use and have a good set of hyperparameters for your task. So this lecture is all about exploring the underlying characteristics or assumptions. So in this lecture, we are going to move towards a modular learning approach, and we will start by looking at a linear regression model, and most commonly used a linear regression model is a least squares regression. So once you build the model, you have to optimize the model with respect to your problem. So there are two ways to optimize problems and train the algorithm. One is using a direct method and other is using a stochastic gradient descent algorithm. You may have the flexibility to employ non-linear models in situations where your model is not able to capture the data with a linear model. Apart from these modifications, you can also use a validation set to improve the model's generalization, and a model which does not perform well on the test data is bound to have poor quality. Therefore, certain techniques such as a regularization method is used to decrease the testing or test phase error. So similar concepts which we will employ in the linear regression can also be incorporated in linear classification. So we will also look at two simple learning algorithms in classification named as perceptron learning and Vinno multiplicative rule. We will also employ some techniques for solving optimization problems in classification, and some of the models are logistic and multinomial logistic regression techniques, which are quite frequently used and in the classification models. So before going into the detail, let's have a simple example to look at. For example, you may be encountered with a decision to choose a restaurant. So in everyday life, we need to make decision by taking into a lot of factors. So in the case of choosing a restaurant, we have four parameters or four features to choose from. So here we have reviews of the restaurant, the amount it costs, the distance it requires us to travel, and the level of cuisine marked at the scale of 1 to 10. So you may have this dataset and you can use this dataset to make a decision about selection of a restaurant. But the most cardinal question here is the selection of the weights that we put on each of these factors. For example, how important are way with respect to others. Some people from you may put a certain weight on to the distance and some may put weights onto the reviews to choose a restaurant. But for a machine learning algorithm, you have to choose the factors and weights so that these weights have minimal error rate. So you have to find out what factors are bad and what factors contribute towards the actual capturing of the data. So we will like to have different weights for each feature and we would like to have minimum errors so that we would have a perfect classifier that captures all of the data insights. So far we have talked about procedures for learning. As in the lecture 2 we discussed about naive-Bayes technique. Then in the lecture 3 we discussed two learning algorithms KNN and Bayesian trees. But now we take a more modular approach. So in this modular approach or in every practical setting in the machine learning domain, you have to specify few parameters before choosing any machine learning task. The first and the foremost choice is the selection of a model describing the relationship between variables of the interest. For example, what model will you employ to choose a restaurant? What factors are more important to you and on what factors you put more emphasis? Secondly, you have to define a loss function. Loss function will quantify how bad is the data fit. For example, the loss function will count the number of errors or the distance between the actual value and the predicted value in terms of regression. Then once you have identified the model and the loss function to measure its performance, you try to fit the model and you use different optimization techniques. And then you choose a regularization method saying how much we prefer different candidate explanations depending upon the performance of the model on the unseen data sets. So by mixing and matching these modular components, your machine learning skills become combinatorically more powerful. So we will start with the discussion of the regression as the core model for this modular approach. So you may recall from the previous lecture, a regression is the prediction of the actual value. In contrast, classification is the prediction of the class label. So in a one-dimensional regression model, we have an example here which shows circles. So circles are the data points. For example, these are the training examples that are given to us. So the data points are uniform into the x dimension, but they may be displaced in the y or the output dimension. So as you can see, you have a linear representation along the x-axis, but the representation along the y-axis is in a non-alien form. So whenever you want to predict a value, you use the input feature vector to and use a function on those input feature vectors to predict the output value. So we have used t and y interchangeably for the output prediction. So in this case, we use the output prediction as a function t of x, which is some function of the input feature vector f of x plus some error. So error is classified as some noise. So if there is no noise into the input feature vector, this noise will be 0 and we have the correct prediction. So in the green is the true curve that we do not know before modeling the data. So our goal is to to fit a curve to these points so that we have a model that correctly translates input feature vectors to the predicted and the actual outcome. So that for the future examples we have a linear or a non-linear method to predict subsequently. So before starting the task on any of the examples, you have to ask few questions. So first question is about the model, and the question should be, how do we parameterize the model, the curve? What learning algorithm should we use and what should be the parameters to that learning algorithm so that we have a learning algorithm in this shape. So once we have agreed on a learning function, then we have to provide an objective measure that how will you check that your learning algorithm is performing as per expectations. So in the machine learning term, you have to specify a loss function or an objective function to choose from, and this objective function will tell you that how accurate your predictions are. So once you have the model and then a loss function to check the performance, you try to minimize this loss function so that your model predicts accurately. And then when you have minimized the error sufficiently on the training example, you check this uh, algorithm or classifier on the unseen test data, and you would like to optimize this fit to the unseen test data, and which is the generalization of your algorithm. And if your algorithm generalized well, you are good to go. And if your algorithm have problem in generalization, you have to employ some regularization techniques to cater the needs. So an example application is provided to you with the lecture material on the CMS. So this example is from the California Housing Census database, and you have to predict the housing prices. So housing prices is an actual value, therefore this is a regression task. So you have to estimate the median house price, and the task here is to use the California census data to build a model of housing prices in the state. So you will use the model and then you will provide use a loss function, and then you will use different techniques to optimize your loss function onto the training data and then generalize on unseen examples. So you can look at different attributes which contribute towards the prediction. For example, you have an attribute of population, median income, district, room, etc. So use this data to predict the median housing price in any district given all other metrics. So once you have the data, the next task is to represent the data. So in the regression case, we want to predict a scalar value t, as in this case, as a function of some scalar vector x input feature vector. So data is described in the pairs of the dimension which can contain input feature vectors and a target values. So as in this case, x is the input feature vector which can contain income, district, bedrooms, etc. for the case of housing data, and the t is the target output which is the median house price. So again, t is continuous because this is a regression problem. So choose the model which outputs a y, which is an estimate of our target value, which is composed of input feature vector multiplied by some weight added with some assumption. So we have input feature vector x multiplied by some weight w1 plus a bias w0. So what type of model did we choose? In this case, we chose a simple linear model. So if we draw the model, our model should look like this. The next task is to divide the dataset into training examples and testing examples. Use the training examples to construct hypotheses or a function approximator that maps this x to the predicted value y. Then evaluate this hypothesis onto the test set. So let's move back to the discussion of the selection of the model. So in the previous example, we chose a simple model which was y of x is equal to w0 plus w1 x. So we have the same linear model here with just few modification in the representation. So again we have w1x. So here we have used wx. So w stands for the number of weights we will use to employ, and these weights will come from a weight space. So how will you find a weight space? That is the discussion in the next few slides. The x is the input feature vector again, and the w0 is replaced with the bias value. So let's interpret again. Y is the prediction of the values used by the input feature vector along with the weights. So W is the weight, B is the bias term, and W and B are together are the parameters to the algorithm, and settings of the parameters is called hypothesis. So here is the formal definition. Again, suppose we have multiple inputs. As in the case of housing data, we will represent these inputs in a feature vector which will start from the x1 first example to the xn last example. So again, we may have different inputs, such as in the housing data we have the input of housing age, population, district, etc. So this kind of problem is often referred as multi-variable problem. So it can have different attributes ranging from x1 to xn and a different coefficients to multiply by each input attribute w1 to wn. So there is no different than the single input case, but it is just little harder to visualize in a two-dimensional space. So again we have linear expression, just we have replaced each feature vector uh, attribute with its corresponding weight. So we will have w1 x1, w2 x2 up to wn xn. So usually you will add one artificial attribute which is x0, and you will multiply it with the weight 0, and combinationally it will be our bias term. Therefore, when you add all of these variables in the linear expression along with an artificial attribute, you will have an prediction y, which is summation of all of the feature vectors with all of the examples from 1 to n. So for the regression case, this will predict an actual value or the predicted value, which will be continuous. On the other hand, if you employ it into a classification method, for example in a binary classification, and if the result of this prediction is greater than 0, the class will be positive, otherwise it will be negative. However, this prediction may be corrupted with some noise. So a simple model typically does not exactly fit the data due to the lack of fit is because of the noise. And there can be different sources of noise. For example, there can be an imprecision in the data attributes. For example, you may have input noise. For example, in the housing data, you have the noise into the population variable or the housing age variable placed wrongly. Therefore, it will affect the actual prediction, and it will be classified as noise. Noise can also be present in the data targets. For example, you may have mislabeled target or noise in the housing prices. For example, you may have some data elements which are wrongly estimated or which have the higher price value than expected. There can be some additional attributes which are not taken into account by data attributes, also classified as noise, and these attributes affect the target values, and often these variables are the latent variables. So in this example of the housing data, what else you could think that could affect the housing prices? For example, there can be the housing prices can range due to the crime rate in specific district. So this can also contribute to the noise. And some in some cases, model may be too simple to account for the data targets. So if you use a simple model which uh, which is unable to capture the information or the insights, will be also classified as noise into the data targets. So one of the most commonly used in the regression model is the least squares regression. So this is again a simple model which is a linear one, and we use the same model as used in the previous slides, which is a function of the x and the weight attributes. So again we have a linear model f of x, y of x, which is equal to w of 0, bias term and weight term with the input feature vector. So once you have defined the model, the next task is to define the standard loss, or in some cases cost or objective function. So there is a slight difference between loss and cost function, which we will understand in the next few slides. So for example, we define a simple loss function that measures the squared error between the predicted value and the true value t. Squared error says how bad the fit is. So a loss is defined as the formula provided here. So which is the difference between actual values and the predicted values, and you take the square to have the positive values. So if you replace the prediction, which is our linear model here, you can modify the formula as provided in the second line. So here t minus y, which is the actual residual error, and we want to make this error as small as possible in magnitude. So cost function is usually a loss function in many cases, but usually a cost function is averaged over all training examples. For example, if you divide this cost function, the loss function with the number of examples n, this will provide you the cost estimation. Now you have a linear model. You have the standard loss function, which will measure the prediction and the actual target difference. That means it will simply measure the errors in the predictions, or in mathematical terms, it will measure the difference between the target values and with the prediction of the models. So if you have chosen a particular hypothesis, for example y of x defined by the choice of any weights drawn into the red. For example, in this case we have chose this hypothesis. So by choosing this hypothesis, we have resulted this model, and we have actual examples depicted here. So the loss function for the red hypothesis is the sum of squared vertical errors, which is the squared length of green vertical lines. So as you can see, these are your predictions. I will highlight, and these are the actual targets. So for the loss function, you have to measure these distances and then minus it from the actual targets to obtain the loss of your model. So once you have calculated each distance, you make the square and then sum it over all of the training example, and the total cost will be the actual cost or the loss of your predicted values, or it will specify how bad is your classifier. So this is the simple regression model, but the problem is how to train it. So if you recall that training a model means setting its parameters so that the model best fits the training set. So in this case, we have to find out the optimal weights. So how do you find the specific weights which decrease these distances to the actual prediction marked into the red? So you have to find out these weights that minimize the loss function. So now we have defined a loss function or a cost function, whatever you call it. The goal is to minimize this cost function or a loss function. So there are various techniques to do that. A simple technique is from the calculus. So if you recall or explore about this technique, that minimum of a smooth function, if it exists, occurs at a critical point, and that critical point is the location where the derivative is 0. So in multivariate generalization, partial derivative must be 0. So the working principle of derivatives or the partial derivatives is beyond the scope of this course, and if you would like to know more about the partial derivatives, I will provide you a link in the reading material so you can explore more about the partial derivatives. So for in our case, we would simply assume that the partial derivative is a method in which we can employ to optimize our algorithm. So suppose we have a function f which consists of number of input features, then the partial derivative, which is uh, displayed or annotated as this form, says in what way the value of this function changes if you increase the input feature vector value by a small amount while holding the rest of arguments fixed. So partial derivative will particularly depend on the partial variable. So for example, if you have multiple variables, the partial derivative with respect to one variable will assume all the rest of the variables as constants, and you will only measure the value of that particular variable of the interest. So for some objectives, you can also find the optimal solution analytically by setting the partial derivatives to 0, called the direct solution. So this is the case for the linear least square regression. So again, partial derivatives are used to optimize the problem, and this technique uses the derivatives of a multivariate function with respect to one of its arguments. For example, if you have multiple variables a, b, c, and you want to obtain the partial derivative of a, b, and c independently, and for each variable, the rest of two variables will be considered as constants. So to compute, you have to take the single variable derivatives pretending the other arguments are constant. So for example, the partial derivative of our prediction y can be calculated with respect to the weights as provided here. So we use again the our prediction or predictor model or linear model, which was wx plus b, and we take the partial derivative with respect to the optimum weights. So in this case, the bias is a constant term and the derivative of the bias is 0, and the W is considered as coefficient, and in this case, if the weight is equal to 1, our partial derivative with respect to weight will be our input feature. However, if we want to explore more and extract the partial derivative of our second variable, which is the bias term, we place the first variable as 0. So once we have x as 0, the partial derivative of the constant is equal to 1. So you can also employ this method to extract the loss function's partial derivative. So you would like to find the value of these weights that minimize the cost function. So we have a chain rule of the derivatives. For example, we would like to have partial derivatives of loss with respect to weights. So if we cannot directly access the loss function with respect to weight, we extract the loss function's partial derivative with respect to the predictions, and then predictive derivative with respect to weights. So as we have calculated the partial derivatives of weight, which is equal to x of j, and we have the loss function described in the previous slide, which was 1 by 2 y minus t whole square. So when you take the partial derivative with respect to weights, you can see we have y minus t into x of j. Similarly, you can find out the partial derivatives of loss function with respect to bias, and in this case our x of j will be treated as 0, so we will have only y minus t. So whatever the case, we just need the partial derivatives to optimize our algorithm. So in the first method, we use the direct solution, and which is a common technique that utilizes the vectorization of the weights and input feature vector. So again, you have the same model, which is the y of x is equal to bias plus weight term and the input feature vector. So let's say we have two weights, in this case bias and weight 1, and we have input feature vector x. So in this first case we will have w1 and the x0, which is represented as when, and x1 represented as x. So in machine learning, vectors are often represented as column vectors, so which are two-dimensional arrays with a single column. So if weights and input feature vectors are column vectors, then the prediction is y of x w of t into x, where w of t is a transpose of weight vector, which is a row vector instead of a column vector. So this term is a matrix multiplication. So you can write the model in a vectorized form by expressing the terms of vectors and matrices. So there are many benefits to vectorize your input feature vectors and weights. For example, the equations and the code will be simpler and more readable. Vectorized code is much faster to execute, and it uses highly optimized linear algebra libraries to execute in Python. And matrix multiplication is also very fast on GPUs, therefore conversion of the matrix into vectorized form is more efficient. So let's look at the further illustration of the previous slide, which is a step further, in which you organize all the training examples uh, into the design matrix X, with one row per training examples and all the targets into the target vector T. So if we take the case of the previous example, we had WT of X. So you had the input design matrix X, and each row in this vector represents one example. So as you can see, we have one example x1 of t up to x3 of t, and we take the transpose to convert the feature vectors into the feature values into the vectors, and then you compute these predictions by adding a bias term and multiplying by the weight factor. So we have WTX for each instance plus some bias term, which will result in our prediction. Again, we will have one matrix for the prediction Y. So you can compute the squared error on the whole dataset and or your square error will be equal to the formula, which is the residual error between the prediction and the actual target squared over and the total divided by total number of examples. So similarly, like the loss function, you can use the partial derivative to obtain the cost function, and the only difference here is that you have to divide by the number of examples. So once you find out the minimum of the partial derivatives, and this minimum should occur at a point where the partial derivatives are zero. However, this is not the case, that you find the actual weights where the partial derivative is exactly zero. So there are the cases where you can find a linear model and you can find the value of these optimal weights that minimize the error. So if the partial derivatives of the cost function is not equal to zero, you should reduce the cost by changing these weights. And there is a simple formula which can be learned from the training examples. So this turns out that this gives a system of linear equations, so which we can solve efficiently. So to find the value of these weights that minimize the cost function, there is a closed form solution, or in simple words, a mathematical equation that gives the result directly learned from the input examples or feature vectors and the target values. And this mathematical equation is called normal equation, and these are the optimal weights which are directly calculated by learning from the input examples. So linear regression is one of the only a handful of the models that permit direct solutions. So this slide shows the illustration of finding out the direct solution or closed form solution. So consider our model which has the number of training instances, which are the n examples. So we have the target values, which is a vector attribute. We have input feature vector, and we have weights. So you can find out the cost or the loss function of the weights provided in the previous slide. So you can use the same formula which we derived for the linear example, which is Wt of x, and then we can extract this from the actual targets to calculate the total loss function. So when you expand this formula, you will get a result in this format, and then you have to find out the partial derivative, and you have to be very clear that the actual solution or the optimal solution is where the partial derivative of the loss function is equal to 0. So you use this loss function and you expand these equations to find out the partial derivatives. So once you have expanded the loss function, you result in this equation, and then take the partial derivative with respect to optimal weights. So when you take the derivative and set it equal to 0, you can find out about the optimum weights. So here the target examples are unuseful for us, therefore these are neglected. So we have taken the partial derivative with respect to weights. So weight transpose will be considered here as constant. So we are left with this equation, and when we take the actual weight, we are left with the same normal equations provided in the previous slide. So that was one way of optimizing a learning algorithm. Now you can use another method, and this is uh, again the minimization of the cost function, but this method is more broadly applicable, and the name of this method is the gradient descent. Gradient descent is a generic optimization algorithm capable of finding optimal solutions to a wide range of problems, and it is an iterative algorithm, which means you can apply and update repeatedly until some criterion is met. So in this case, we initialize the weights to something reasonable. For example, you can use all weights as 0 and then repeatedly adjust them into the direction of steepest descent. So gradient descent is much similar to the hill climbing algorithm, but it works in the reverse direction. Therefore, it is the descent rather than ascent. So again, it minimizes the loss function or the cost function. So if we represent it geometrically, you would like to have a function which will gradually decrease its value. So the basic rule of the gradient descent is to initialize the weights, for example, randomly, and then repeatedly update these weights based on the gradient. And you can use this formula to update the weights, which is the weight is equal to weight minus some learning rate and the partial derivatives of the loss. So here you observe the same value, which is the partial derivative of the loss function or the cost function, and if that is greater than 0, then if you slightly increase the weights, it will increase the cost, and if it is less than 0, and then if you slightly increase the weight, it will decrease the cost function. So the following update decreases the cost function, assuming a small enough learning rate, and the learning rate is often signified as lambda or alpha. So you have used the same formula to you update the weights, and in this case we employed the partial derivative of the cost function. So again, you have to choose a very precise value for the learning rate, because the larger the learning rate is, the faster the weight changes, because this value will be a greater value if the learning rate is higher. So we will later see how to tune the learning rate, but the values are typically very small, for example ranging between 0.01 or 0.0001. So as the error approaches to 0, so does the update W stop changing. So this mechanism or this behavior gets its name from the gradient. So therefore, gradient descent updates the weights in the direction of fastest decrease. So why will you use the gradient descent if we can find the optimum solution directly using the first method? So first of all, gradient descent is a much sophisticated algorithm, and it can be applied to a much broader set of models. Gradient descent can also be easier to implement than a direct solution, especially with automatic differentiation software. For regression in high-dimensional spaces, gradient descent is more efficient than the first method or the direct solution method. Matrix inversion in the direct solution method is a big O of d cube algorithm. However, there are some problems associated with the gradient descent which are not the part of this lecture, and we will cover those problems in a separate lecture. We will explore more about the working of gradient descent. But there is a one issue which we discussed in the previous slide. It is about the learning rate, and the learning rate affects the convergence and the errors. For example, if you set a significantly larger learning rate, this will have a greater probability that the error or the convergence of the algorithm is faster, but the error on each epoch will be more higher, and there will be also possible oscillation. For example, your weights may jump from here to here if you have a very high learning rate and back to here, etc. So there will be problems for uh, managing oscillations and errors. On the other hand, if you set a small learning rate, the convergence will be slow. That means the weight changes, the value in the weight changes will be very insignificant, but the error will be also insubstantial. Therefore, you have to set a learning rate which is quite below to impact the sudden change of the weights. So to implement the gradient descent, you have two methods to generalize this for all of the examples in the training set. The first method is to use a batch gradient descent. So instead of calculating the partial derivative for each example, you calculate the partial derivative for a set of examples called a batch or a batch update. So sum or the average updates across every example n, and then you have to change those parameters. So this is where the choice of learning rate is more important. So you have to multiply the learning rate with the cost to find out the approximate weights for the batch. But there are some problems with the batch gradient descent, that it uses more or some part of the training examples as a whole to find out the optimal weights. Therefore, calculating gradients over a set of examples makes it very slow. Therefore, there is an alternative, which is stochastic or online gradient descent update, which updates the parameters for each training case in turn according to its own gradient. So this method randomly shuffles the training examples in the training set, and it updates the weight for each training example picked randomly. Therefore, working on a single example makes it much faster than the batch processing. However, there are some cases when you come to know that your data is more complex than a straight line, or you may have the situation when you know that your linear model is not good enough to capture the details. So how can you create a more complicated model? So for example, we take the same case and we are unable to capture the green line. For example, our model predicted this line and it has a significantly greater amount of residual error or the cost estimation. So you will like to have a more robust or more powerful model. So do you need to derive a whole new algorithm for this, or on the other hand, do you need to tweak the input parameters to capture these details? So you can create a more complicated model by defining the input variables that are combinations of components of the feature vector. So one option is to fit a low degree polynomial model instead of a linear model. This is known as polynomial regression. So for example, instead of simple method which was w0 plus w1x, we used a polynomial expression of 3 degree, which is w3x cubed, w2x2, x squared, w1x plus w0 to capture more complex patterns. So for example, you can use an mth order polynomial function of one-dimensional feature x. So our function will be similar to the previous function which we used for linear regression, which was w0 plus w1x. So just in this case, we have a multiple input feature representation of the same input feature vector. That means we can use different powers of input features or different combinations of input features. So in this example, we have x of j, w of j, where x of j is the jth power of x and w of j is the feature vector for weights, or in polynomial terms the coefficients. For example, we can have 9x plus 6x squared as a polynomial model. So we can use the same approach to optimize the weights. Just like the previous approaches, we can employ a direct method or gradient descent. But before employing those methods, we have to convert these input combinations to a feature map which is similar to the input feature matrix. So as you can see, we have employed a third order polynomial, and the order of the polynomial is the highest degree present in the polynomial expression. So we get the polynomial regression model, which is WT, and a feature map of input feature vector. So which is much closer to our previous representation of the linear model, which was WT and X. So you can see there is one difference. In the linear vector, we had the linear representation of input features. On the other hand, in a polynomial regression method, we have a feature map of input here. Again, rest of the derivations and algorithms for this remain exactly the same. So there are two types of linear models that are equivalent with respect to learning. So first we specified the linear model, which was WTUX, and then we have a more complex model which consisted of the feature maps, WT feature map of these input attributes. The first model has the same number of adaptive coefficients or the weights as the dimensionality of the data. For example, if we have the training example of the Johnny liking the pie, if you recall, we have 5 attributes or 5 dimensional data. So our first model will result in 6 coefficients. 5 for input feature attributes, and the sixth term for the bias. However, if we employ a more complex model, which is the second model in this case, it has the same number of adaptive coefficient as the number of basis functions. That means if we have used the same pi example and we have combined the first two attributes of those pies and limited our features to a total of four vectors attributes. So our second model will result in those basis function plus a bias attribute term. So once we have replaced the data by the outputs of the basis functions, fitting the second model is exactly same problem as fitting the first model. So using our new notations for the basis function, linear regression can be written as in the similar fashion as the linear model, just we have the feature map here. So Phi can be either the input example itself for multivariate regression or one of the non-linear basis functions. So in simple terms, it can be an example of a linear equation such as 9x plus 6, or it can be a combination of these examples in form of non-linear basis function such as 3x square plus x plus 9. So once again, we can use the least squares to find the optimal solution, and then deriving the optimal weights, we can get it from the same principle of the normal equation. You can find different methods or different basis function to capture the complexity of your model or the data. So typical examples are using a sigmoid function or Gaussian function or some polynomial expression. So you have used or seen the polynomial expression in the previous slide. Here are the examples of sigmoid functions and the Gaussian functions. So you may recall from the lecture 2, Gaussian is the representation of continuous variables under a hyperbolic curve where the concentration of the sample is centered at a mean. Similarly, uh, sigmoid is a similar function. There is a minute difference between those two functions, and sigmoid employs uh, another mapping function. So if you have a complex data, you can use these kinds of model basis functions. So for example, we had the same data and we can use the different polynomial models to capture the model details. So if you examine the first case, we have 0th order polynomial, that is our model is equal to only the bias term, which is constant throughout the example. So as you can see, we have the model representation of a red line. However, our actual representation or our desired representation should be the green line. So you can see there are many errors. So there will be a higher cost or loss estimation. So in machine learning term, this is the underfitting. This means the model is too simple. That means it does not fit the data or it does not capture the details. Similar is the case for the first order polynomial, which is the linear equation w0 w1x, and again it is a straight line which have different errors. So if we use the third order polynomial, as you can see, the highest degree is 3. It is the third order polynomial, and you can see the cost function is minimized. As you can see, the red line is very close to many points and there are only few errors. So you can increase the degree of polynomial to capture or reduce these errors. So for example, you used a ninth order polynomial where you have the highest degree of 9, and it models all of the points. That means there is no training error and your model is able to capture all of the training points. So will you say that this is the perfect model? Most oftenly this is the not. This is a result of overfitting. That means the model is too complex and fits very perfectly, however, it will not generalize. So these are the two problems. If your model is too simple to capture the details, your model has the underfitting problem, and if your model is too complex, it will have the overfitting problem. So this is just an illustration of the previous concepts. That means you can combine different features to create a feature map, and then you can feed those results to a linear classifier to predict the actual value. So now take a recap. You have picked a data set, then you picked a model, then you use the model to capture the details, and if there were some losses or cost estimation problems, you used one of the optimization techniques such as a direct method or the gradient descent to optimize your model, or even used a combination of a more complex model such as a different basis function or a polynomial expression to capture the details. So at this point you have trained the model, and now you would like to generalize this model for the new data. So this step is the generalization of your model. So generalization is the model's ability to predict on the held out dataset. That means the test dataset. So what is happening here, if you picked from the previous slide a model with the degree of 9 which overfits the data, and it also includes models model's noise, that means it captures the noise as well as the correct training examples. So as you can see, we have error posted here with respect to the degree of the polynomial. As you can see, the training error is decreasing as you are increasing the degree of the polynomials. Similar is the case for the test example. But as you have moved to a more complex model and your model is also modeling the noise, your training error is likely to increase to a substantial level. And a good measure is to use an acceptable level of uh, complex model so that your generalization is not uh, underfit or overfit. So as in this case we used root mean square error. So here is the formula to calculate the errors, which is the estimation of the model's value with difference from the actual target. So the division by the n for the root mean square error allows us to compare different sizes of datasets on the equal footing, and the square root ensures that the error root mean square is measured on the same scale and in the same unit as the target variable t. Generalization have a close link with the number of training examples and the parameters to the model. So generalization problem is tractable problem if we have lots of training examples. So for example, a complex model with few examples will not be able to capture the details and it will overfit or underfit. And if the model is complex, it is more likely to overfit with less amount of training data. Similar is the case, we have more examples and our model will generalize better. The training and the test error as a function of training examples and parameters is also generalization. As you can see, if you increase the training example, the training error is likely to increase after few times, but this will have a inverse effect on the test error, which will reduce on the new examples. However, if you are making your model more complex, your training error will likely to decrease, but your test error is likely to increase after some time because your model is more complex than the data. That means it is modeling the noise as well. So this regression has illustrated some key concepts. So first of concept is the data fit. You have to ask a question where your data fit. Is the choice of linear model is suitable, or you have to choose a more complex model. So for example, if you have chosen a linear model but your data is more complex, it will not capture all the important variations or signals in the data. This will result in underfitting. On the other hand, if your model is more complex, it may overfit the training data. That means it will not fit only the signal but also the noise data, especially if not enough training examples constrain the model. So there is one method for assessing your fit, that is test generalization, which is the model's ability to predict on the held out data. And optimization is essential, so you can use stochastic or batch iterative approaches or analytical approach, which is the direct method whenever available. So let's look at the estimated weights for again number of different degree polynomials in the case of fewer examples. So we have a case where examples are significantly lower and the model is significantly complex. So the weights are becoming huge to compensate. As we can see, if we had the linear models, the weight had a very controllable limit. But as you can see, you are increasing the degree of polynomial, the weight values are, are becoming out of control and you have reached the 9-level polynomial. Then you can see there are enormous valued weights. So one way of dealing with this is to encourage the weights to be small. This is this way the no input dimensions will have too much influence on the prediction, and this method is called regularization. So in the case of polynomial, the degree of polynomial is a hyperparameter that is just like the k in the k nearest neighbors algorithm. So we can tune it using the validation set, which is a technique to control the overfitting phenomena. So in this way, you divide the training sets in three examples. The first is the training examples, the second is the test examples, and third are the validation examples. So first you choose the model, train it onto the training examples, and optimize using those training examples. So before generalization onto the test examples, you validate those data onto the validation examples and make any regularizations required to the model, and then on test on the remaining test examples. So one way is to one method of controlling the overfitting is to reduce the complexity of the model. But restricting the size of the model is a crude solution, since you will never be able to learn a more complex model even if the data support it. So as you can see, we have a model represented in the red line with the higher order polynomial. So a similar polynomial model is represented in blue line, which is more suitable choice. That means it is complex enough to capture the details, but not complex enough to even model the noise. So in this way, you have chosen another approach, which is keeping the model large but regularizing it. So you use the regularizer, which is a function that quantifies how much we prefer one hypothesis versus the another. So it is just a comparison of two similar hypotheses. So in the observation, polynomials that overfit often have large coefficients. So if you remove or try to reduce these coefficients or weights to a smaller value, you have a better chance of reducing the generalization error. So we can encourage the weights to be small by choosing our regularization with the L2 penalty. So we add a term to the cost function so that our model is regularized. So note, to be more pedantic, the level to norm is a Euclidean distance. So we are really regularizing the squared level to or L2 norm. So you add this penalty term to the error function in order to discourage the coefficient from reaching a large value. So again, the hyperparameter learning rate controls how much you regularize. So the regularized cost function makes a trade-off between fit to the data and the norms of the weights. So again, you can choose a very precise learning rate, and this learning rate is a hyperparameter that you can tune using the validation set. So usually there are two types of regularization: the ridge regularization provided here. There is a lasso regularization, and there are elastic net. Ridge is just a squared of your weights. On the other hand, it is L2 form of regularizer. The lasso is L1 form of regularization, which means it will not have the square. On the other hand, elastic net used both forms of techniques, and elastic nets employ whichever the best one. So as you can see, by controlling the learning parameters, you can control the amount of weights or coefficients for each type of polynomial. So the corresponding coefficient from the fitted polynomial showing that regularization has the desired effect of reducing the magnitude of the coefficient. So this will reduce in the training set and the test set error. So this concludes our discussion about the linear regression, and we can say that the linear regression exemplifies the recurring theme of this course, in which you have to choose a model and a loss function to capture the errors of those model predictions, and then formulate an optimization problem, and then employ uh, technique from direct solution and a gradient descent to solve the optimization problem, and then you can use the different methods to employ these techniques. For example, vectorization is one form to represent the terms into the linear algebra to make the processing or representation more efficient. And then you can improve the generalization by using a regularization method. So similar concepts can be applied to the classification techniques, and if you recall, classification is the prediction of a discrete valued target instead of continuous valued target. So if you take the binary classification, you have to predict a binary target which is between 0 and 1. So training example with the target is equal to 1 are positive examples, and training example with the target is equal to 0 are negative examples. So again, if you use the linear model which we used in the linear regression, and the model is the linear function of x followed by a threshold bias. So again we have wtx plus d. So if you eliminate the bias, you use a dummy variable which is x0 and which is always equal to 1. Therefore w0 is equivalent to bias. So we have generalization of the linear vector, sorry, the linear function, which is g is equal to wtx. So our prediction y will be 1 if our method z results greater than our threshold result, and 0 if it is less than our threshold. That means it is 1 if you have provided a probable value with your estimation. If you look geometrically, the same is the case for the regression. We have training examples which are the points in the geometry, and in the linear regression you have to model to predict the actual continuous values, and to find out the cause is the difference between the values and the estimation. However, in the classification you have the decision boundary, which is the boundary to differentiate between positive and negative examples or different kind of examples. So in the two-dimensional it is just a line, but think of it as a hyperplane. So in the examples, if the examples can be separated by a linear decision rules, they are linearly separable. As you can see in the first example, we can separate the positive and the negative examples with blue line. However, some datasets are not linearly separable. So if you take the second example, it is very difficult or even impossible to use the straight line to separate positive and negative example, and you can use some kind of this method or model to separate positive and negative example. So if you use the simple method, this is a linear method, and if you use a complex method, it is a non-linear method. So if we take the linear method, linear expression, uh, for example, in this case, is based on this data, which separates the positive examples from the negative examples. We have three negative examples and one positive example specified by this linear method, which is a linear expression and whose sign decides about the example class. So if the result of this class expression is positive, then the class is positive, and if the result is negative, the class is negative, and if it is the opposite, it is the error. So similar to the regression, you would like to have weights for prediction in classification. So the first step for the classifier is to initialize the classifier weights. Again, use the random weights, but in this case, we have provided limit between -1 to 1. So present a new training example to your classifier and label this example by the classifier, obtaining the prediction, which is referred here as h of x. So if our prediction is not equal to the actual target or label, you have to modify the classifier's weight, and unless the termination criteria is satisfied, you have to keep repeating this loop. So there are two simple rules. If your prediction is equal to 1 and the actual target is equal to 0, you have to reduce the weights of attributes with all of the input attributes where value is positive. On the other hand, if prediction is 0 and target is 1, you have to increase the weights with the attributes which have the value equal to 1. So this is an additive formula, and it is widely used in one of the known machine learning algorithm, which is the perceptron learning. So you employ a weight learning additive formula, which is the calculation of weights and adding with a term of a learning rate and the difference between actual and the predicted outcome multiplied by the input feature vector. So if actual and predicted values are same, the weight will not change because this difference will result in a 0, and therefore weight will be same. So again, if prediction is 1 and actual is 0, weights are reduced, and if prediction is 0 and weights are 1, weights are increased. So the formula increases or reduces the weights as required or leaves them unchanged. But you have to consider that only attributes weights will be changed where the attribute value is present, and amount of change is controlled by the learning rate, which is between 0 and 1, preferably a lower value, so that your algorithm converges slowly but accurately. So here is a numerical example to exemplify the perceptron learning algorithm. So examples are described by the attribute x1 and x2 and labeled with the class cx. So prediction is 1 if summation of all our linear model is greater than 0 and prediction is 0 otherwise. So let's take a very higher learning rate because we have very few examples. So learning rate is equal to 0.5, and as we have specified in the previous slide, that take the weights uh, randomly. So we have taken the weights between -0.1, and the weights are positive 0.1, 0.3, and 0.4. So as you can see, we have used two weights for two input feature vectors, which are W1 and W2, and the weight 0 for the bias term, and consider the example E1 and the label of E1 which is equal to 0. So hence the prediction is equal to 1, because if we use these weights, the value is 0.4, which is greater than 0. So then you employ the previous additive formula to update the weights. So as you can see, in the first case your value was 4.1, and then you update the weights, the value is 0.2 and then minus 0.4. So in this case you have the prediction as negative class. So again, there is the explanation of the numerical example. As you encounter with the first example, you had three weights specified: 0.1, 0.3 and 0.4. You have the prediction and the actual value, and the difference between prediction and the actual value. So the prediction was 1, the actual was 0, the difference is -1, therefore the weights should decrease for example 2. So the weights, as you can see, you employed the same formula, additive formula, to calculate the weights, and the weights were reduced in the second classifier. So the and remember, the weights were only reduced for the bias term and the first attribute, because the second attribute is 0, therefore it will not have any effect, therefore W2 is unchanged. And then you proceed with the E2. Again, E2 is 1 1, therefore prediction is 0 and actual is 1. Again, there is a difference of 1, therefore weights should increase. So in this case, all of the weights are increased. And in the third case, you can see there both of the examples, all attributes are 0 and prediction is 0, and we see prediction is 1 and outcome is 0 and difference is -1. Therefore attributes weights should decrease again, but this time you can see only the W0 is decreased. So similar to the learning rate into the regression, the perceptron and learning jumps are quite visible because the learning rate was very high. So as you can see, the four consecutive versions of the classifier from the previous slides are shown, and in the first example, when the weights were initially assigned, we had the linear separation here. But once we changed the weight of the first classification, it jumped from here to here, which is a quite significant jump. And then we again changed the weights and our algorithm jumped back here and then finally here. So as you can see, after a few modifications, the algorithm is less likely to jump high. Therefore, choosing a lower learning rate will reduce these kinds of jumps and errors. So here are some comments about the perceptron learning algorithms. The perceptron learning algorithm is guaranteed to find a solution if the two classes are linearly separable, and the different values of initial weights will lead to different learning behaviors. That means it may take longer to change weights if the learning rate is low, and the lower learning rate can make the learning process less jumpy but perhaps too slow. Similarly, if there are more attributes, learning usually takes longer than. Another principle which is similar to perceptron learning is the multiplicative rule, and it is known as Winnow algorithm. In the previous we had used the additive formula, but in this case we use the multiplicative rule. That means multiply the weights instead of adding or subtracting. And here we use the coefficient alpha, which controls the learner's sensitivity to errors, which is similar to the learning rate in perceptron learning. Here is the requirement that alpha should be greater than 1. Typically alpha is placed at 2. So we calculate the weights with the formula of W of I multiplied by alpha power the difference between the predicted and the actual outcome. So initial weights are assigned to 1 and the threshold of weights is n minus 0.1, and n stands for number of attributes into the examples. So the prediction is 1 if your estimation is greater than this threshold value. So let's move back our discussion to the loss function of the classification. And if you recall the binary classifier that predicted the binary targets between 0 and 1, our estimation was the linear model of WTX plus B, and prediction was 1 if it is greater than a threshold and 0 if it is less than the threshold. So what happens if you are not able to classify the training examples correctly? Much similar like the regression, it is the loss or error or cost estimation. But seemingly obviously, the loss function here is the 0-1 loss instead of a value loss. Therefore, you calculate the loss or 0-1 loss with respect to your prediction and the target, and your loss will be 0 if your prediction and the target is equivalent, and it will be 1 if these are not equivalent. So as like regression, the cost is the average loss over the training examples. For 0-1 loss, this is the error rate. So you count all of the errors and divide by the training examples to calculate the total loss. So after the modeling, the next problem is using the optimization method. So in the case of classification, partial derivatives of the loss 0-1 is 0 everywhere it is defined, and the partial derivative of 0-1 is equal to 0 means that if you change the weights by a very small amount, it will have no effect onto the loss, because loss is measured in terms of 0 and 1, not into the value. And if your loss does not change to the threshold, it will be considered same. For example, if the loss is 1 and you have the threshold to specify that the example should be classified as 0 to 0.5, and you are currently standing at 1, and to reduce these values to a significant margin, you have to change the weights to a high proportion. Therefore, uh, changing the weights will not have significant effect on the loss. Therefore, the loss function hates when you make the correct predictions with high confidence. Therefore, if the target is 1, it is more unhappy if your prediction is 10 than if your prediction is 0 or 1. So as we discussed in the first lecture, there are many methods and regression algorithms that can be used for classification as well. And logistic regression is one of the commonly used method to estimate the probability that an instance belongs to a particular class. Hence, there is obviously no reason to predict the values outside 0 and 1. So we have to squash the prediction into the interval 0 and 1 as depicted in this graph. So the logistic function is a kind of sigmoidal function or an S-shaped function. So the sigmoid function is represented in the equation here. So sigmoid function says that it is just like a linear regression model. This model computes a weighted sum of input features plus a bias term. So much similar like the previous model, we have Wt of x. So much similar here, we use the theta term, which is Wt of x. So the prediction is again h of 0 or h of w, and we employed a sigmoidal function, which is the logistic activation function, to predict the actual value. So this function outputs a number between 0 and 1. So a linear model with a logistic non-linearity is known as log linear. So used in this way, the sigmoidal is a, is called a activation function, and the output is called the logit. So because the prediction is between 0 and 1, we can interpret it as the estimated probability that target is 1 or not. So the objective of the logistic regression is that in the training is to set a parameter vector so that our model estimates higher probabilities for positive instances. That means where y is equal to 1 and the target example is equal to 1. And your model should predict low probabilities for negative examples, which is equal to where y is equal to 0. So here is the cost function for logistic regression, which is minus log of p if prediction is 1 and minus log of 1 minus p if prediction is 0. So this cost function is very useful because minus log of probability grows very large when your target approaches to 0. So the cost function will be large if a model estimates the probability close to 0 and the actual target is close to 1. So this again it works on the probability of your prediction. So the cost will be large if model estimates a probability close to 0 for a positive example, and it will be very large if the model estimates a probability close to 1 for a negative example. So the cost function over the whole training set is the average of the cost over all training instances. It can be rendered in a single expression called the log loss. So problem here is that there is no known closed form normal equations to compute a value that minimizes the cost function. The good news is that the gradient descent is here and it can be used just like any other optimization algorithm. The gradient descent is guaranteed to find the global minimum if the learning rate is not too large and you wait long enough. Just like other linear models, logistic regression models can be regularized using L1 or L2 penalties. Softmax regression is another classification model, and the logistic regression model can be generalized to support multiple classes, which is the softmax regression, without having to train and combine the multiple binary classifiers. This is often referred as multinomial logistic regression or MLR in short. That means you do not have to provide separate classifier to distinguish between different classes or labels. The idea is simple. When given an instance X, the softmax regression model first computes a score f of x for each class K, then estimates the probability of each class by applying the softmax function, also called the normalized exponential, to the scores. So here is the formula to calculate the softmax estimation. As you can see, there is a slight difference as we have number of examples. So our previous formula was the xt into w, and in this case we have k number of examples. Therefore we have k estimates for each class provided into the training example. So you compute the score for every class for instance X, then estimate the probability that the instance belong to class K by running the scores through softmax function. The function computes the exponential of every score, then normalizes them, dividing by the sum of exponentials. The scores are generally called logits or log odds, although they are actually unnormalized log odds. Once you estimate the probabilities and make prediction, the objective here is to have a model that estimates high probability for the target class and consequently a low probability for the other classes. So minimizing the cost is called cross entropy. It penalizes the model when it estimates a low probability for a target class. Cross entropy is frequently used to measure how well the set of estimated class probabilities matches the target classes. So you can measure the cost for number of classes and over the training examples. So again, the um, cost estimation is provided in terms of loss function, and you can see the loss function decreases if your actual predictions are equal to 1 and the actual targets are equal to 1. So if you are unable to predict them correctly, the cost is likely to increase. On the other hand, if you correctly predict the negative examples or the other classes, the cost function is decreasing and it will likely to increase when you misclassify. So this concept of the binary cross entropy loss can be incorporated in multi-class examples as well. So if we have two classes, this function is similar to the cost function to the logistic regression cost function or the log loss. So that is the end of this lecture, but I would like to suggest you to go through the lecture code provided with this file onto the CMS, and you should also try to tackle the Titanic dataset, which is a great place to start on Kaggle. So Titanic dataset is a dataset of the individuals who were on board of the Titanic ship and the number of people survived. So you have to predict the survival chances based on their input feature vectors. So go onto the Kaggle and follow this link and tackle the Titanic dataset. And also, if you want to learn more about the topics covered in this lecture, you should read the chapter 4 of the Introduction to Machine Learning reference book, or you can use the section 3.1 from the pattern recognition and machine learning book to understand more about the closed form solution. And additionally, the chapter 4 is also useful for understanding some concepts about logistic regression and the linear regression as well. And on top of that, reading material provided along with this lecture is quite beneficial to understand the basic modular approach of selecting the model, optimizing the model using using a cost or a loss function, and then employing a regressor regularization to meet the generalization objectives. So that the end of the lecture, and if you have any questions, please ask me through any of the designated mediums or conduct a question and answer session. Thank you very much.